Hello, and welcome to the third and final lecture on Chapter 6 material. Now, as we've discovered, Chapter 6 deals with some more complicated versions of force stuff. We've talked about friction, we've talked about centripetal force, and I'm going to spend a little bit, at least here at the beginning, talking about the drag force. Now, I don't want to spend too much time talking about it. It's actually an incredibly complicated subject. And today's lecture is not going to be that long. That said, uh, the drag force is a consequence of viscosity. Okay, so if you've ever, for example, poured things like maple syrup, if you've taken your hand and you've run it through water and felt a resistance to it, say hand through the water. If you've ever taken your hand and stuck it out of the window while a car is driving, you feel a resistance. Let's say hand in wind. Okay. Now, specifically, let's think about this one because I think this is probably one that everyone's done. If you take and you put your hand out of a window and you put the palm facing forward, you feel a lot of drag. You feel a lot of force being applied to your hand. But if you turn it sideways, it goes down. Okay. Now, so it turns out that as air or water or any other fluid passes around something, it also drags across it. And that drag is called viscosity. Now, the thing that is dragging across doesn't have to be a solid. It could be another fluid as well. For example, if you were to mix oil and water, you would have viscous flow at the interface between the oil and the water. Now, that said, the form of this force that's generated by this drag typically is proportional to the velocity, or it's proportional to the velocity squared. Okay. Now, which one is it? Well, it depends upon the characteristics of the fluid and also depends upon the characteristics of the thing that's dragging through it. Now, that said, a good example of one of these things would be, let's look at the v squared one. So the drag force, when you have something that is subject to a force that goes like velocity squared, looks a little bit like 1/2 c rho a times v squared. Now, this is the force. And what I want to point out is that it is a force that is a function of velocity. Okay. Now, so the C contains important information about the fluid, specifically its properties with respect to viscosity. And it may not be a constant, it may not be a scalar. For example, in my experience, when I dealt with viscous flow in complicated stuff like plasmas, this was actually what's called a tensor. Okay, so it can be complicated. It's an incredibly complicated subject. Now, this rho thing is a volume density. Okay, it's the amount of mass per unit volume you have. Okay, so that's a density. This is what's called the cross-sectional area. It's the cross-sectional area of the thing that's moving through the fluid. Now, what do I mean? Well, if this is your fluid right here and you're moving something like this through it in this direction, this area, if the direction is this way, it's this area that whose face is in that direction, we say that the surface normal is in the same direction as it, that's the cross-sectional area. So for example, your hand, if you open it palm first into the wind, has got a huge amount of area, right? That's a hand, I guess. Looks almost like, I don't know, Bart Simpson maybe? I'm not entirely sure. But if you turn it sideways, what you do is you reduce the amount of area that's present, and what that does is in turn cause the force to go down. So like I said, this is actually a pretty complicated thing here. And typically what we do is we call this string of constants right here B or C, depending upon what's going on. We'll call this one B. B is 1/2 C times rho times A. Okay, so you would say that the force here, at least in this particular form, would be equal to B times V squared. Okay, but sometimes the drag force looks like, it's proportional to just V. All right. Typically, in cases like that, we say it's equal to C times V. And C looks a little bit different just because of the units and because of what's going on. And like I said, this is actually an incredibly complicated subject. And I don't want to spend too much time talking about it except to show you how, you can deal with situations like, for example, terminal velocity. Now, so what's meant by terminal velocity? Well, I'm glad you asked. So we know in a free fall situation, when something falls, it's falling strictly due to the force due to gravity. So in free fall, you only have one force present. That force is weight. It's a consequence of something's mass, being affected by the acceleration due to gravity, which I'm going to call g vector. Okay, now, but if you look, for example, at this viscous force right here, this drag force. This drag force is just like any other frictional force. It opposes, the direction of motion. So, for example, if you had something falling this way, down this way, you would have, by merit of the fact that you're moving through air, a viscous force that goes up like that. Okay, so you would call this, we'll say, the drag force, F sub d, and this right here would be the force due to gravity. Now, what I want to point out here is this this viscous force is a consequence of velocity. Well, I mean, it's not a consequence of velocity, but it depends upon velocity. It's a consequence of viscosity and all this other stuff. So anyway, so what this means is that as you fall, as you move faster and faster and faster due to the force of gravity, you have more and more of your motion taken away from you because of this drag force. And there is a point in which the drag force here completely balances out the force due to gravity. Okay, so at that point, we say that you're at terminal velocity. So at terminal velocity, what's happened is the drag force and the force due to gravity have balanced each other out such that you're experiencing no net force at this point. So what that means is that you've reached a velocity that you're going to fall at basically at a constant rate. Okay, so just to pick an example, you have this one right here, this form, which is the v squared one. You fall faster and faster and faster, and eventually, and let's just write the form of this drag force up here. Okay, eventually you hit the speed in which this force is exactly equal to, the force due to gravity on your object. So we'll call that speed v sub d. All right. So at that point, what's happened is you've reached this point of cancellation. We'll say, and that's the condition right there. So you could find this drag force if you wanted just by solving for it, right? So, and if you do that, you end up with something that looks like this right there. So here's the equation, that you would deal with if you wanted to find, what the terminal velocity was of something that was falling, through air. Now, or heck, moving through water or anything like that. And the important thing is, again, the C thing has got the characteristics of the fluid that you're moving through. And you also have the density of the fluid that you have to take into account as well. This area is the area that's being presented, by the thing that's moving through the fluid. Okay. And as you can see, the bigger the area, the smaller the drag, or the smaller the drag velocity. So, for example, if you were a person who was, skydiving, without a parachute, which I wouldn't be surprised if that was the next big sport, your cross-sectional area, if you were to sort of point your feet straight down, you would be like a lawn dart. You would hit the ground going incredibly fast. Okay. If you lay your body out like this, what you do as you fall is to create a bigger area. Okay. And then if you were to do the smart thing, well, I'll say the second smartest thing. The smart thing is to attach a parachute to yourself, because now this right here is the cross-sectional area right here. So your chute is what allows you to fall. Okay. And, not hit the ground like a bullet, basically. Now, the first smartest thing is to just simply not jump out of a plane. But, that's just my opinion. So, like I said, I just wanted you guys to get a feel for what this drag force was like. We're not going to do anything really with it, except maybe calculate one or two examples of what the terminal velocity would be. And if you're honestly interested in learning more about it, the best thing to do would be to move on past University 2 into something like classical mechanics and take a class in which it's addressed full-fledged. Even in classical mechanics, we have to make a lot of assumptions because of the complexity of the way drag works. So that said, let's just move on to one or two examples that I wanted to cover. I know this is a little disjointed, but I feel like just to kind of tie everything together, we should at least talk about these types of problems. So what I wanted to do was two examples that show you how things can, or at least forces can work together. And in this particular one, what we have is somebody attempting to push a metal plate, and then you have a coefficient of static friction because the plate obviously is sitting on the ground, and also a coefficient of kinetic friction, because the question is does the plate move? And if it does, what acceleration are we looking at? All right. So that said, let's draw a picture. So here is, we'll say, the floor like that. And here's Y, here's X. Maybe here's our metal plate right here. I'll put it like this. And what I want to do is to exert a force on this plate, we'll say to the right like that. This is the force of my push. It is 200 newtons straight down the x-axis. Okay. Now the plate, we know, has weight, or has mass. As a consequence, it's got weight. So there's a weight vector, and then there's the normal force right there. So here's the force due to gravity right there on the plate. And then this is the normal force right there. Okay. Now the mass of the plate here is 20.0 kilograms. This would be a 45-pound plate if you've ever gone to the gym. Okay. Now, the coefficient of static friction here is 0.75, and once it gets moving, you have a coefficient of kinetic friction that looks like 0.35. We are told that the plate starts at rest. I'm going to assume that our initial position in X is also at 0, just because of the way I've drawn it. And I think this is probably just about all the information that we have. Okay. Now, so we have a couple of questions to ask. First says, does the plate move? And if it does, what acceleration does it experience? Okay. So let's just look initially here at what's going on with respect to the plate. Let's draw a force diagram. So here's y, here's x. Okay. Now I'll just add this to my picture as well. We do have this frictional force that's a consequence of us trying to push on it. And I'm just going to call this cursive F for right now. Okay. So in this case, the question we're asking for part A is that when I push this thing this way, do I have enough static friction generated to prevent this push from moving it? Now, that friction is going to be a consequence of, at least because of the way the problem is, the weight of the plate pushing to the ground and creating a normal force. Okay. So we have the force of our push. We have, in this case, the static frictional force. We have a normal force, and then we have the weight. Okay. Now, like many of the problems that we've worked in the past, we're going to sum up the forces here rather to get the net force. Okay. And we have four forces present. We have a normal force. We have the weight. We have the force of our push. And then we have the static frictional force. And what we want is where everything exactly balances itself out to zero. Now, clearly, the normal force and the gravitational force are going to do that. This plate doesn't bounce or anything funny like that as we push it to the side. But the question here is that when I calculate what the static frictional force is, and I compare it to this push, does the static frictional force, is it greater than or equal to the push? Or is the push greater than the static frictional force? If this is the case right here, then it's going to move. Okay, that means I'm pushing harder than static friction can give me. And then I can move on to part B. Okay, so this is really the question that we need to address here with this. Okay, so as you can see, let's just work what's going on in the y direction. We have a normal force that points up. We have the weight that's down, and those are going to balance each other out, like I said. And then in x, we have the force of our push minus the static frictional force. And the question is this greater than zero? Okay. If the push is greater than the static frictional force, then this difference is going to be greater than zero. Okay, so that's a big question. Now we're going to need information from this one right here in order to do this one right here, because we do know that the weight is m times g, and we do know that the static frictional force has the form of mu sub s times the normal force, right? But we'll come back to that. Let's go ahead and write out our givens. So what are we given? We have a mass of 20.0 kilograms. Our initial position is 0. The coefficient of static friction is 0.75 kilograms. Oh, it starts from rest, which means our initial velocity is 0, 2. And we also have a coefficient of kinetic friction, which we may or may not need, which is 0.35. The force of our push is 200 newtons, and we're going to have this force just go straight down the x-axis. Okay, so there are givens. What are we trying to find? So for part A, we want to find, does the force of the push exceed the static frictional force? If it does, then it moves, and we can move on to part B. For part B, we want to find the acceleration and also its position after 4 seconds. So that's additional information right here. 4 seconds into the future is where we'd like to look if we end up using that. So that said, let's get on here. So if I take the equation here in y, I have that the normal force minus m times g is equal to 0. So that's going to tell me what the normal force looks like, right? For the equation here in x, we have Fp, which is the push, if you will, minus the static frictional force, which looks like mu sub s times the normal force. And the question is that greater, than 0? So let's just go ahead and flesh this out a little bit. F sub p minus mu sub s mg. Is this greater than 0? Well, we can find that out real quick because we know the force of our push is, 200 newtons. Mu sub s is 0.75 kilograms. The mass of the plate is 20.0 kilograms. Actually, this is not kilograms. Sorry about that. What I'm doing right there. That's unitless constant. Thinking about the mass. And, G is 9.8 meters per second squared. So if I actually do this difference here real quick, 0.75 times 20 times 9.8. I can already tell you that it's going to be positive. Yes, 53. So 53 newtons. So what this says is my push is definitely going to move this thing. So does the plate move? You bet. Sure does. It moves. Okay. Now, so so it's moving. So what acceleration does this thing experience? All right. Well, I'll tell you what. Let's put another page in here, and what I'm going to do is to take my picture right here and sort of transpose it over here. Let's copy it. We'll paste it right here. There we go. Okay, so now what we have here is this being F sub k. Since we know this thing is going to move, we're going to push on it, it's going to break free, and then it's going to slide, but the frictional force that we experience is going to be less because now we're in, the kinetic friction, zone. So if I draw my force diagram over here, it's going to look the same as the other one, really, except instead of, having static friction, it'll have kinetic friction. So this is y, this is x. We've got the push to the right. We have the kinetic friction to the left. We have a normal force that goes up, and then we have a weight that goes down. Okay, so normal force, weight, force of the push, and then kinetic frictional force. Okay, so now if I add up the forces to get the net force, of which I have 4, I have a normal force, I have the force due to gravity, I have the force of the push, plus I have my kinetic frictional force. That's going to equal to m times a. Okay, because we know it's going to experience a net force along x. All right. So in the y direction, the normal force and the weight, just like the previous thing that we did, they cancel each other out. In the x direction, though, that doesn't happen. What we have is a push to the right. We have our kinetic frictional force to the left, but that's going to act on our plate to cause it to experience acceleration. All right. Now, again, we know gravity looks like m times g, and we know that our kinetic frictional force looks like mu sub k times the normal force. So what that means is if you look at this one right here, the normal force is equal to m times g, which means that this right here, which is mu sub k times n, is really equal to mu sub k times m times g. So what I have is that F sub p minus mu sub k mg is equal to m times a. That's this equation right here. So if I want to know what the acceleration is going to look like, right? And this is acceleration in the x direction. I should be specific about that. Just be clear. Okay. So if I look at the acceleration here in the x direction, if I divide both sides by the mass, what I end up with is F sub p over m minus mu sub k times g. This right here is going to be the equation for my acceleration. But it's constant, right? Because mu sub k is just a number, g is just a number, the push is a constant, the mass is a constant. So what that means is that I can use my kinematic equations here, right? So I have, Vx is equal to V naught x plus Ax times t. I have x is equal to x naught plus 1/2 Ax t squared plus V naught x times t. And then I have Vx squared minus V naught x squared is equal to 2 Ax x minus x naught. Okay? Now, so we're trying to find, if you go back here and you look at this, we're trying to find the acceleration and also its position, after 4 seconds. So what that means is if we go ahead and solve this one right here, this is 200 newtons divided by 20.0 kilograms minus 0.35 times 9.8 meters per second squared. If I solve for my acceleration here, I'm going to get, let's see here, I get 6.57. So this is 6.57 meters per second squared. Okay. If I want to find out where it's at after, 4 seconds, I would use this equation right here because we know our initial velocity is 0. We know our initial position is 0. So x is going to equal to 1/2 a sub x times t squared, which would equal to 1/2 times 6.57 meters per second squared times 4.0 seconds squared. So if I do that, it's 52.56. Okay, so at the end of the day, our acceleration, if you look at the sig figs, specifically through this one right here, is 1. So our acceleration is about 7 meters per second squared. And where's this thing at after 4 seconds? Well, it's about 50 meters to the right. Okay. So just an interesting example to show you, how motion works when you have more than one oppositional force at play. We'll do another one. A person of mass 75 kilograms stands on a scale in an elevator. If the elevator accelerates upwards at 1.5 meters per second squared, what does the scale read? If it accelerates downwards at 1.5 meters per second squared, what does the scale read? What would the scale read with the elevator at rest? Now, this is a big hint because scales read the normal force. Okay, when you get on a scale, it doesn't tell you how much you weigh, it tells you how much it's pushing back on you. That's the reason why if you stand on a scale and you sort of jump up and down real quick, you'll see the needle fluctuate pretty strongly. And that's a consequence of this. It's not telling you your weight, it's telling you the normal force. So what this says is that if you want to lose weight, all you have to do is to get an elevator, potentially. We'll see. So what I'm going to do here is to break this up basically into scenarios. I'm going to call this first one scenario A. This is scenario B, and this is scenario C. Okay, so this is A, this is B, and this right here is C. Okay, now in all cases, we have the same mass. So we're given, and I'm just going to break this up into the parts here. The mass here is 75 kilograms, but the acceleration for the first part, it says upwards. I'm going to call upwards positive 1.5 meters per second squared. The second one says downwards. I'm going to call downwards negative 1.5 meters per second squared. Okay. And for the third one, as you can see for part C, it's at rest. And if it's at rest, that means the acceleration, at least the net acceleration, is going to be 0. And that's what I'm looking at, is the net acceleration here. Okay. So let's just look at part A here. So here's our elevator right here. Here's a scale on the bottom. Here's our person. There's some weird looking head right there. Okay. Now, so in this case, for part A, the elevator is accelerating upwards. So there you go. The net acceleration is 1.5 meters per second squared in the positive y-hat direction. But the person inside the elevator still has a weight, right? So they have a weight that's down, right? It would be minus mg y-hat, right? Now, if you were to look at this person in here, you'll also notice that because they're standing on the scale is pushing back on them. There's a normal force, like that. So if I were to draw a force diagram, on this person inside the elevator, there's a normal force that's up. There's a weight that's down. But I'm going to put off here on the side the fact that the net motion is upwards. So that's where your acceleration is. Your net acceleration is up. Okay. Normal force, force due to gravity. Okay. So if I were to look at this and sum up my forces to get the net force, I have two. I have a normal force and I have a weight. Okay. These are going to add together to act on the mass on the person inside there and produce an acceleration. The acceleration is going to be 1.5 meters per second squared. All right. Now, in the x direction, nothing interesting. In y, though, there's a lot interesting. You have a normal force that points up. You have a weight that points down. And this is going to act on the mass of the person to cause that acceleration. Now, what we want here is what the scale reads. And scales, like I said, read how much they're pushing back on you with. So they read normal forces. So in this case, the normal force, which is what the scale is going to read, is going to equal to MA minus the weight. Now the weight here, though, is just M times G, which means that this is equal to MA minus MG, or if you look at it, M times A minus G. Okay, so hold on, it's a math error. A plus G. Sorry about that. I had to step back. I was like, what's going on here, man? There. Okay. Sorry about that. I'm going to let that stand because everybody needs to know that even we make errors too. So, 75 kilograms times 1.5 meters per second squared plus 9.8 meters per second squared. And when you take and you do this, this says that the normal force is 11 1102 or about 1103 newtons. Now, I'm not going to round this yet. I'm just going to take and I'm not even going to box it because I want to get that inclination there. We'll put a little arrow beside here to tell us that this is what you see for part A. Now, for part B, the solution is basically, or at least the process is basically the same as part A, except now, the elevator is going down, right? So in this case, the acceleration is downwards at 1.5 meters per second squared. Okay. And, I can probably just snipe this. I'll tell you what, let me do that. Just like that. Copy, paste, move it over here, just like that. Like I said, the acceleration's changed. So let me whip out my eraser and fix that. Like that. There, now it looks the same. Okay. So now, and for this one though, your acceleration is downwards, like I said. So now the acceleration that you experience on the inside is minus 1.5 y hat. Excuse me. So here, when you draw your free body diagram, like this, and this is the y direction, this is the x direction. You got a normal force that goes up, right? You got a weight that goes down, but the net acceleration is down like that. Right? So here, when you sum up your forces to get the net force, you have a normal force that points up, you have a weight that points down. And that's definitely not going to be equal to 0, right? So if you take into account directions, obviously in the x direction, nothing interesting is happening. But in the y direction, what you have is a positive normal force, a negative weight, and then your acceleration is down, so it's negative. Okay? So here, the normal force would be equal to minus ma plus mg, putting in what the weight is, or m times g minus a. That is 75 kilograms times 9.8 meters per second squared minus 1.5 meters per second squared. So when you work this one, it's 622.5, about 623. Now, what this does is to explain the phenomenon that you feel whenever you get into an elevator. When you get into an elevator and you go up, you feel like you weigh more. Now, you don't weigh more. What's happening is because of the acceleration of the elevator upwards and the fact that your feet are in contact with the floor of the elevator, when the elevator and you accelerate upwards, your inertia says, hey, I want to stay where I was before. So as a consequence, your feet push into the floor and the floor pushes back on you with the normal force, which makes your feet tell your body, tell your brain that, hey, I weigh more because I have to support more weight. When you go down in an elevator, the acceleration is downwards and you feel like you weigh less. And that's because the downwards acceleration is causing the floor of the elevator to push on your feet less. Okay. Now, if you compare this to what it would be if we were just looking at your weight inside the elevator, which is exactly what this is right here. Well, I think we can all agree that for part C, what's going to be read is simply just the weight, right? So 75 times 9.8, 735. So 735 newtons is what you would quote unquote weigh, if you were, on the ground, not experiencing any net acceleration at all, right? And that would be your true representational weight, at least here on the Earth. So if you wanted to keep this to 2 sig figs, for part A, it would be about 1100 newtons. For part B, it would be about 620 newtons. And for part C, it's going to be about 740 newtons. Okay. Now, so this is it. This ends our lecture sequence for Chapter 6. And I'll see you in Chapter 7 material.